What if I told you that right now, at this very moment, something from another star system is racing away from Earth at over 40 miles per second and we'll never see it again? On December 19th, 3, I-Atlas made its closest pass to our planet, coming within 168 million miles of us. But here's what makes this impossible to ignore. This isn't a rock that belongs to our solar system. It came from the space between stars, visited us once, and now it's leaving forever. So where is it going? What happens when an interstellar traveller crosses back into the cosmic void? And what did we learn in the brief moment we had to study it? Stay with me for the next few minutes because we're going to follow 3i Atlas on the journey it's taking right now, trace the path it will travel through our solar system and beyond, and explore what happens when something truly leaves forever. Think about that for a second. We spend so much of our lives dealing with things that come back. People leave and return, seasons cycle. Even most comets that visit our inner solar system are on elliptical orbits, meaning they're bound to the sun, destined to swing back around eventually. Some return every few years, others every few centuries, but they return. We can predict their arrivals, prepare our telescopes, watch them come back like old friends visiting from distant neighbourhoods. But 3i Atlas isn't like that. Its orbit isn't an ellipse. It's a hyperbola, an open curve that doesn't loop back. It came from interstellar space, passed through our solar system once, and now it's heading back out into the galaxy. This is a one-time encounter, a cosmic one-night stand, if you will. And the question everyone's asking now, the question that carries a strange weight, is simple but profound. Where is it going? Before we follow that path, if you've been with us through the entire story of this interstellar visitor, if you want to know where it's heading now and what its future holds in the cosmic ocean, hit that like button. Drop a comment telling me, did you watch the December 19th flyby happen in real time? Or are you catching up now on what happened while the world was distracted by holiday preparations? Because this isn't just about an object leaving our solar system. It's about understanding what happens after the headlines fade, after the telescopes move on to other targets, after the excitement settles. It's about following something to the end of the story, or rather, to the beginning of a much longer story that we won't be around to witness. Let's be honest about what December 19th meant. For weeks leading up to it, astronomers and space enthusiasts tracked 3i Atlas as it approached Earth. Not dangerously close, of course. It passed at a distance of about 28 million miles, which in cosmic terms is a decent margin. But it was close enough to study in unprecedented detail, close enough to capture images that revealed its structure, its jets of gas and dust, its behaviour as an active visitor from beyond our solar system. Observatories around the world pointed their instruments at this traveller. Amateur astronomers set up their backyard telescopes. Social media filled with photos and real-time updates. There was excitement, curiosity, even a touch of nervousness for those who didn't fully understand the numbers. And then the day came and went. 3i Atlas made its closest approach to Earth, continued on its path, and the immediate drama was over. But here's what most people miss. That closest approach wasn't the climax of the story. It was the pivot point. Imagine watching someone walk toward you from a great distance. You watch them get closer, closer, until they pass right by you, maybe exchange a glance, and then they keep walking. The moment they pass you isn't when they disappear, it's when they start moving away. And for a while, you can still see them. You can still watch them go. You might even turn around to keep them in view for as long as possible, but eventually they're too far away, obscured by distance or obstacles, and they're gone from your sight even though they're still walking, still moving, still existing somewhere out there in the world. That's where we are now with 3i Atlas. We're in the watching it walk away phase. We can still see it, though it's getting fainter every day. We can still track it, though it's getting harder. We can still study it, though the window for observation is closing. And that's the beautiful, bittersweet part of this story. We're not dealing with something that exploded or crashed or vanished in some dramatic fashion. We're dealing with something that's simply leaving, moving away at tens of miles per second, continuing a journey that began long before our solar system was even a point of interest on its path. If 3i Atlas could somehow perceive its surroundings, if it had any awareness of the journey it's been on, December 19th would have been just another day. Another gravitational field negotiated, another star system sampled and left behind, another brief detour in an odyssey that spans timescales our minds struggle to comprehend. We were the ones marking the date on our calendars, adjusting our telescopes, staying up late to catch a glimpse. For 3i Atlas, we were just a momentary increase in brightness on one side, a slight tug of gravity that barely altered its course, a brief interruption in the endless dark. But that's the thing about cosmic events. They don't care about our need for drama or closure. They don't arrange themselves for our convenience or emotional satisfaction. They simply happen according to the laws of physics, the momentum imparted billions of years ago, the gravitational dance of objects in space. And we, fragile and temporary as we are, get to witness tiny slices of these vast processes. We get to point our instruments at the sky, gather photons that have bounced off distant objects, and piece together stories about where things came from and where they're going. That's what we're doing now. We're piecing together the next chapter, the one that doesn't involve us anymore except as observers, watching something fade into the distance. So where is 3i Atlas right now? As you're reading this, as you're processing these words, 3i Atlas is somewhere beyond Earth's orbit, moving away from both the Sun and our planet. Its speed relative to the Sun is high enough that nothing in our solar system can slow it down or capture it. The Sun's gravity is pulling on it, yes, but not strongly enough to curve its path back inward. Think of it like throwing a ball into the air. If you throw it gently, it goes up and comes back down. That's an elliptical orbit. But if you could throw it fast enough, it would escape Earth's gravity entirely and never come back. That escape velocity from Earth's surface is about 7 miles per second. 3i Atlas is travelling faster than the escape velocity of the Sun's gravity from its current position. It's got enough speed to break free, to leave the Sun's influence behind, to return to the space between stars. Every second that passes, 3i Atlas is getting farther away, not in a dramatic, accelerating fashion, but in a steady, relentless way. Picture the distance growing like an invisible thread stretching between us and the object, a thread that gets longer and thinner and eventually breaks when the object becomes too faint for even our best telescopes to detect. Right now, that thread is still intact. Astronomers are still tracking it, still gathering data, still measuring its position and brightness. But they know the clock is ticking. They know that within weeks or months 3i Atlas will cross a threshold of visibility, will become too dim against the background of stars, and we'll lose it. Not because it's stopped existing, but because the cosmos is vast and light has limits, and our instruments can only do so much. And that's the part that gets me, the part that carries an emotional weight I didn't expect to feel about a chunk of rock and ice. We're watching something leave that we'll never see again, not in our lifetimes, not in 1,000 lifetimes, not ever. Humanity had one chance to observe 3i Atlas up close, and that chance is now in the past. The data we collected, the images we captured, the measurements we made, that's all we get. There's no return visit, no second chance to study it with better instruments or answer the questions we didn't think to ask. It came, we saw it, and now it's leaving. And once it fades from view, it becomes a memory, a set of numbers in a database, a series of scientific papers, a brief chapter in the ongoing story of interstellar objects visiting our solar system. But the object itself keeps going. That's the profound part. Our observation of it ends, but its journey continues, and that journey, the path it's taking right now and will take for millions of years to come, is what we're about to explore. We're going to trace that path, follow 3i Atlas through the outer reaches of our solar system, watch it cross boundaries that only a handful of human-made objects have crossed, and imagine what lies ahead in the vast emptiness between stars. We're going to confront the reality of cosmic timescales and distances that make human history look like a blink. And we're going to find meaning in the fact that we were here, briefly, to witness a visitor from the infinite. So let's turn around and watch it go. Let's follow 3i Atlas on the outbound leg of its journey and understand where it's heading now that Earth is receding in its metaphorical rearview mirror. Because this is the part of the story that matters most, the part that reveals what happens after the world stops watching. To understand where 3i Atlas is going, we need to quickly trace where it's been. Not in exhaustive detail, but enough to orient ourselves in the journey. Because trajectory is everything here. The path it took to reach us determines the path it's taking to leave us, and that path was set in motion long before humans existed. This isn't a course correction story. There's no pilot adjusting the route. There's only momentum, gravity, and the geometry of space. 3i Atlas entered our solar system from interstellar space, from the vast emptiness between stars where objects drift for millions of years without encountering anything significant. It came from a specific direction in the sky, from a region in the constellation of Ursa Major, though that's a human construct, a way of organizing the celestial sphere that means nothing to the object itself. It was traveling at high speed, fast enough that the Sun's gravity couldn't capture it into a bound orbit. As it approached the Sun, it accelerated, as all objects do when falling toward a massive body. It swung through the inner solar system, passing closest to the Sun on October 29th, a moment called perihelion. That was when solar heating was at its maximum, when jets of gas and dust erupted from its surface as frozen materials sublimated in the sudden warmth. That was when it became brightest, most active, most visible from Earth. After perihelion, 3i Atlas began the outbound leg, moving away from the Sun but still approaching Earth because of the geometry of orbits. We weren't at the closest point to the Sun when 3i Atlas was. We were farther along in our own orbit, so even though 3i Atlas was moving away from the Sun after October, it was still approaching us, closing the distance until December 19th, and then it passed us. That's where we are now, in the aftermath of that close approach, watching it continue outward. Think of the solar system from above, an imaginary vantage point high above the plane where the planets orbit. You'd see the Sun at the centre, the planets tracing their elliptical paths around it, and 3i Atlas, cutting through the whole system on a hyperbolic trajectory. It came in from one side, curved around the Sun, and is now heading out on a different side. The path doesn't loop. It's like a slingshot maneuver, except gravity isn't slinging it anywhere specific. Gravity is just bending its path as it passes through. The object came in with a certain velocity and direction. The Sun's gravity altered that direction but couldn't trap it, and now it's leaving with a different direction but still high velocity. If you could draw the trajectory in 3 dimensions, it would look like an open curve, entering from infinity, passing through the solar system, and exiting to infinity again. And right now, 3i Atlas is somewhere along that outbound curve. It's already beyond Earth's orbit, moving through the space between Earth and Mars. Every day, it gets farther from both the Sun and Earth. Every week, it crosses distances that would take human spacecraft years to travel. It's moving at tens of miles per second, a speed that sounds fast until you realize how vast space is. At that speed, it would take about 5 months to travel from the Sun to Earth if it were moving in a straight line. But it's not moving toward Earth anymore. It's moving away, outward, toward the outer planets and the edge of the Sun's influence. The strange thing about tracking objects in space is that we're always observing the past. The light we see from 3i Atlas left its surface minutes ago, depending on how far away it is. When you look at an image of 3i Atlas taken today, you're seeing where it was, not where it is. By the time that light travelled to Earth, was captured by a telescope, processed into an image, and viewed by your eyes, the object has moved. It's farther away now. It's continuing a journey that happens in real time, uninterrupted by our observation of it. That delay, that gap between the object's actual position and where we see it, is a small reminder of the fundamental truth of astronomy. We're always looking backward in time, always chasing light that has already left its source. But despite that delay, we can predict where 3i Atlas is going with remarkable precision. Orbital mechanics is one of the triumphs of physics. Given an object's position, velocity, and the gravitational influences acting on it, we can calculate its future trajectory. We can map out where it will be in a month, a year, a decade. We can predict when it will pass certain milestones, when it will cross the orbits of the outer planets, when it will leave the Sun's gravitational dominance. These predictions aren't perfect because there are small forces we can't account for perfectly, like the pressure of sunlight or the subtle effects of outgassing. But they're accurate enough to paint a picture of the journey ahead. And that journey is long. We're not talking about a quick trip to the edge of the solar system. We're talking about years just to reach the orbit of Neptune, decades to reach the heliopause, the boundary where the Sun's influence truly ends, and beyond that, millennia and millions of years drifting through interstellar space. But let's not get ahead of ourselves. Right now, 3i Atlas is still in what we might call the inner middle solar system, the region dominated by the Sun's light and heat, where planets orbit and where human telescopes can still resolve it as more than just a point of light. This is the observable phase, the time when we can still follow its journey directly. Every observation made now is precious because the window is closing. Telescopes around the world are still pointing at 3i Atlas, still gathering data, still measuring its brightness and position. Amateur astronomers with decent equipment can still see it, though it's fainter than it was during closest approach. Professional observatories are tracking it as it moves through the constellations, watching it shift against the background of distant stars. Each night of observation adds to the dataset, refines the trajectory calculations, gives scientists more information about this visitor from beyond. But everyone involved knows this is temporary. Soon, maybe in a few weeks, maybe a couple of months, 3i Atlas will become too faint for most telescopes. The largest observatories might track it for a bit longer, but eventually even they will lose it. And then the direct observation ends. But the journey doesn't. That's the part we need to internalize. When 3i Atlas fades from our view, it doesn't stop existing. It doesn't vanish or dissolve or cease its motion. It simply becomes invisible to us, too small and too far away to reflect enough sunlight back to our instruments. It keeps moving, keeps travelling, keeps following the trajectory that physics demands. And that's where imagination and calculation take over. That's where we shift from direct observation to understanding the journey through the lens of what we know about orbital mechanics and the structure of our solar system. So let's follow that trajectory. Let's trace the path 3i Atlas is taking right now, and we'll take in the months and years ahead as it moves through the outer solar system and begins the long journey back to the stars. Because understanding where it's going means confronting the scale of the cosmos in a way that daily life never requires. It means sitting with numbers that dwarf human experience and finding meaning in the fact that we can even conceive of such journeys. The outer solar system is a different world from the one we inhabit. Down here on Earth, the sun is bright and warm, a dominant presence in the sky that defines our days and seasons. But as you move farther out, past Mars, past the asteroid belt, into the realm of the gas giants and beyond, the sun becomes smaller, dimmer, less influential. It's still there, still the gravitational anchor around which everything orbits, but its light is weak and its heat is negligible. This is the region 3i Atlas is entering now, a region where planets take decades to complete a single orbit, where temperatures plunge to hundreds of degrees below zero, where sunlight is so faint that high noon looks like twilight on Earth. Right now, 3i Atlas is somewhere beyond Earth's orbit, moving outward through the space between the inner rocky planets and the outer gas giants. Over the coming months, it will cross the orbit of Mars, though Mars itself won't be anywhere near 3i Atlas when that happens. Orbits are like lanes on a circular track, and just because an object crosses a lane doesn't mean it encounters whatever is travelling in that lane. The timing has to align, and in this case, it doesn't. Mars is somewhere else in its orbit, oblivious to the interstellar traveller passing through its orbital path. Same will be true for all the outer planets. 3i Atlas will cross their orbits, pass through the regions where they travel around the Sun, but it won't come particularly close to any of them. This is a solo journey, a path determined by the velocity and angle it had when it entered the solar system, not by any intentional navigation. After crossing Mars's orbit, 3i Atlas will continue outward toward Jupiter. Jupiter is the giant of our solar system, a planet so massive that it contains more mass than all the other planets combined. Its gravity is strong enough to perturb the orbits of comets, to capture objects into its own system of moons, to influence the structure of the asteroid belt. But 3i Atlas is moving too fast for Jupiter to do much of anything. There might be a slight gravitational nudge if the trajectories happen to bring them relatively close, but we're talking about a minor adjustment, not a course-altering encounter. 3i Atlas has escape velocity from the solar system. Jupiter's gravity, as strong as it is, isn't enough to capture something moving that fast. So 3i Atlas will pass through Jupiter's orbital region, maybe get a tiny gravitational tug, and continue outward. The same will be true for Saturn, Uranus, and Neptune. These are massive worlds, each with their own gravitational influence, each with complex systems of moons and rings. But 3i Atlas is on a trajectory that treats them as bystanders. It's not here to orbit these planets or get captured into their systems. It's here to pass through, to cut across the solar system on its way back to interstellar space. And each planet it passes represents another milestone in that journey, another marker of increasing distance from the Sun and from us. When 3i Atlas crosses Neptune's orbit, it will be about 30 times farther from the Sun than Earth is. At that distance, the Sun looks like a bright star, not a disk. Sunlight takes over 4 hours to travel from the Sun to Neptune's orbit. The environment is cold, dark, and utterly hostile to life as we know it. But beyond Neptune, there's another region, one that's even more remote and mysterious. It's called the Kuiper Belt, a vast zone of icy bodies that extends from Neptune's orbit outward to about 50 times Earth's distance from the Sun. This is where objects like Pluto reside, where countless small worlds made of rock and ice orbit the Sun in relative obscurity. These are leftovers from the formation of the solar system, material that never coalesced into a planet, remnants of the primordial disk that surrounded the young Sun. The Kuiper Belt is sparsely populated despite containing millions of objects, because space is vast and the objects are small and far apart. You could travel through the Kuiper Belt and never come close to anything, and that's exactly what 3i Atlas will do. It will pass through the Kuiper Belt over the course of years, crossing this region at tens of miles per second, unlikely to come anywhere near any of the resident objects. There won't be a close encounter, no collision, no dramatic event. Just silent passage through a region of space that humans have barely begun to explore. We've sent one spacecraft through the Kuiper Belt, New Horizons, which flew past Pluto and then visited a smaller object called Arakoth. That's it. One spacecraft in a region that spans billions of miles. 3i Atlas will be the latest traveller through this territory, though unlike New Horizons, no one is controlling its path or gathering data from it directly. It's on its own. The journey through the outer solar system will take years. We're not talking about a quick pass. From the time 3i Atlas crossed Earth's orbit to the time it crosses Neptune's orbit will be several years, and during that entire time, it will be getting fainter, colder, less active. The Sun's heating will diminish to almost nothing. The jets of gas and dust that made it visible and active during its close approach will shut down as there's no longer enough solar energy to sublimate the frozen materials on its surface. 3i Atlas will become a dark, inert rock, barely distinguishable from the other cold objects in the outer solar system except for its trajectory. It's moving through, not orbiting. That's the key difference. Everything else in the Kuiper Belt is bound to the Sun, travelling in elliptical orbits that keep them in the solar system forever. 3i Atlas is just passing through, a visitor that won't stay. And as it moves through this region, we'll lose the ability to observe it, not all at once, but gradually. First, amateur telescopes will lose it, then smaller professional telescopes, then medium-sized observatories. Eventually, only the very largest telescopes on Earth or space-based telescopes might be able to detect it, and even that will become questionable as the distance increases and the object's brightness drops. There will come a point, maybe months from now, maybe a year, when the last observation of 3i Atlas is made. Someone, somewhere, will capture the final image, record the final data point, and after that, the object will be too faint, too far, too insignificant against the vastness of space to be seen again, and that moment, whenever it comes, will be a quiet ending to the observable phase of this story. But think about what that means. The last observation doesn't mark the end of 3i Atlas. It marks the end of our ability to witness its journey directly. The object will still be there, still moving, still following the laws of physics through the outer solar system and beyond. It will cross Neptune's orbit whether we see it or not. It will pass through the Kuiper Belt whether we're tracking it or not. It will continue outward toward the boundary of the Sun's influence whether any human ever thinks about it again or not. Our observation is irrelevant to the object's existence. We're just witnesses for a brief window of time, and then the object continues its journey in darkness, unseen and unacknowledged by anyone. There's something humbling about that. We spend so much effort tracking these objects, studying them, extracting meaning from their motions, and then they leave. They move beyond our reach, beyond our instruments, beyond our ability to know what happens to them. We're left with the data we collected and the knowledge that somewhere out there, the object still exists, still travels, still participates in the cosmic dance. But we're no longer part of that story. We've been written out not through any dramatic exit, but simply because distance and light and the limitations of our technology exclude us. And 3i Atlas continues, indifferent to our exclusion, following a path carved out by gravitational interactions billions of years old. So as we imagine 3i Atlas moving through the outer solar system, crossing the orbits of the giant planets, passing through the Kuiper Belt, we're imagining a journey that's real and ongoing but invisible to us. We're picturing an object we can no longer see, travelling through regions we've barely explored, heading toward a boundary that marks the edge of everything we consider part of our solar neighbourhood. And beyond that boundary lies something even more vast and empty, something that challenges our ability to comprehend distance and time. Let's talk about what's happening to 3i Atlas as it moves farther from the Sun, because this isn't just about distance, it's about transformation. The object we observe during its close approach to Earth is not the object that's travelling through the outer solar system right now. It's changing, shutting down, becoming something different as the environment around it changes. When 3i Atlas was near the Sun, passing through perihelion in October, it was active. Solar radiation was heating its surface, causing frozen materials like water ice, carbon monoxide and carbon dioxide to sublimate directly from solid to gas. That outgassing created jets, plumes of gas and dust that erupted from the surface and formed a coma, the fuzzy cloud that surrounds the nucleus of an active comet. Some of that material was pushed away by the pressure of sunlight and the solar wind, forming a faint tail. This activity made 3i Atlas bright and visible, a dynamic object that telescopes could study in detail. It wasn't just reflecting sunlight like an inert rock, it was actively throwing off material, glowing with both reflected light and the faint emissions from excited gas molecules. But as 3i Atlas moves farther from the Sun, that activity is winding down. The intensity of sunlight decreases with the square of the distance. If you double your distance from the Sun, you receive 1/4 the light. If you triple the distance, you receive 1/9 the light. 3. E-Atlas is now several times farther from the Sun than Earth is, and that means the sunlight hitting it is dramatically weaker. There's less energy available to heat the surface, less energy to drive sublimation, less energy to power the jets and coma, so the outgassing slows, the jets become weaker, less frequent, and eventually stop altogether. The coma dissipates as there's no new material being added and the old material drifts away. The tail fades because there's nothing left to push away. 3i Atlas transitions from an active comet to an inert object, a dark nucleus no longer surrounded by gas and dust. This transition is gradual, not sudden. It's happening right now as 3i Atlas moves through the space beyond Earth's orbit. With each passing week, the object becomes a little less active, a little more dormant, and with that decrease in activity comes a decrease in brightness. Brightness for objects like this depends on two main factors: how much sunlight they receive and how far they are from the observer. As 3i Atlas moves away from the Sun, it receives less sunlight, so there's less light to reflect, and as it moves away from Earth, the light it does reflect has to travel farther to reach our telescopes, spreading out over a larger area and becoming dimmer by the time it arrives. Both factors work against visibility. The object is fading from our view, not because it's physically shrinking or disappearing, but because the geometry of distance is working against us. Imagine watching a car drive away from you at night. When it's close, you can see the car clearly, maybe even read the license plate if the lighting is right. As it drives away, it gets harder to see. The headlights become dimmer, the details blur. Eventually it's just a faint glow in the distance and then it's gone, not because the car stopped existing, but because distance has rendered it invisible to your eyes. That's what's happening with 3i Atlas. It's still there, still moving, still reflecting what little sunlight reaches it, but the light reaching our telescopes is getting fainter every day. And there's a threshold, a limit to how faint an object can be before our instruments can no longer detect it. That threshold depends on the telescope, the exposure time, the quality of the night sky, and the sensitivity of the detector. Large professional telescopes can detect much fainter objects than small amateur scopes. Space-based telescopes can avoid the interference of Earth's atmosphere and detect even fainter things. But every telescope has its limit. Below a certain brightness, the object becomes indistinguishable from the noise, from the random fluctuations of light in the detector, from the faint glow of distant background galaxies. When 3i Atlas drops below that threshold, it vanishes from observation. Right now, we're in the window where some telescopes can still see it and others can't. Amateur astronomers with backyard setups have probably already lost it. It's too faint for most consumer-grade equipment to pick up, especially from light-polluted areas. But professional observatories are still tracking it. Universities, research institutions, space agencies, they're still gathering data, still adding to the record of this interstellar visitor. Every clear night is an opportunity to capture another image, to measure another position, to refine the trajectory calculations just a bit more. These observations are valuable not just for understanding 3i Atlas specifically, but for understanding interstellar objects in general. Every data point helps build a picture of what these visitors are like, how they behave, what they're made of. But the clock is ticking. Within weeks, maybe a couple of months at most, 3i Atlas will become too faint for most professional telescopes. The largest observatories in the world, places with mirrors tens of meters across, might be able to hold on a bit longer. Space telescopes like Hubble or the James Webb Space Telescope could theoretically detect it for even longer if they chose to dedicate time to it, but telescope time is precious and there are competing priorities. Eventually the decision will be made that 3i Atlas is no longer worth tracking, that the scientific return on continuing observation is too small to justify the use of these powerful instruments, and at that point, even if the object is technically still detectable, it will fade from active study. There's a bittersweetness to this fading. We had months to study 3i Atlas while it was bright and active. We gathered an enormous amount of data, more than we've ever had on an interstellar object at close range. Scientists will be analysing that data for years, publishing papers, refining models, comparing it to other comets and interstellar visitors. But there's always a wish for more time, more observations, better instruments, clearer skies. There are questions that won't get answered because the window closed before we could ask them properly. There are measurements that would have been useful but weren't prioritised because we thought we had more time. This is the nature of astronomy. You observe what you can when you can, and then the opportunity passes. And once 3i Atlas fades below the detection threshold, our relationship with it changes. We shift from direct observation to retrospective analysis. We shift from tracking a real-time event to studying a historical one. The object becomes part of the archive, a set of images and spectra and measurements stored in databases around the world. It becomes a subject for scientific papers, a reference point for future studies, a chapter in the ongoing effort to understand our solar system and the objects that visit it. But it's no longer something we can point a telescope at and see. It's a memory, a ghost, a set of numbers representing something that still exists but is no longer accessible to us. The last observation of 3i Atlas will be made by someone, somewhere. Maybe it will be a routine data collection session at a major observatory. Maybe it will be a dedicated effort by a team that wants to push the limits of their instruments to see how long they can hold on. But whenever it happens, that final image will be the end of the visual record. After that, everything we know about 3i Atlas's ongoing journey will be based on calculation and extrapolation. We'll know where it should be based on its trajectory, but we won't be able to confirm it. We'll predict when it crosses certain boundaries, but we won't witness those crossings. The object will continue its journey in darkness, unseen by the species that briefly watched it pass. And that's the reality of cosmic exploration. We get glimpses, snapshots, brief windows of observation, and then the cosmos moves on without us. We're constrained by the speed of light, the sensitivity of our instruments, the size of our telescopes, and the vastness of space. We do the best we can with what we have, and we accept that there's so much we can't see, can't measure, can't know. 3i Atlas is teaching us that lesson again, reminding us that the universe is full of things happening beyond our ability to observe them, journeys unfolding in the dark that we can only imagine. So as 3i Atlas fades from view, as the last telescopes lose their ability to track it, we're left with the knowledge that somewhere out there, beyond Neptune, moving through the Kuiper Belt, an object from interstellar space is continuing its journey, and that journey is about to take it across a boundary that very few things have ever crossed. There's a boundary in our solar system that most people don't think about, a line that marks the edge of the sun's influence, the place where our solar system ends and interstellar space begins. It's not a sharp edge, not a wall or a physical barrier. It's a transition zone, a region where the environment shifts from one dominated by the sun to one dominated by the galaxy. And 3i Atlas is heading toward that boundary right now, moving outward at a speed that will carry it across that threshold in a matter of decades. This boundary is called the heliopause. The name comes from helio, meaning sun, and pause, meaning boundary or stopping point. It's the place where the solar wind, a constant stream of charged particles flowing outward from the sun at hundreds of miles per second, finally runs into the interstellar medium, the thin gas and dust that fills the space between stars. The solar wind creates a bubble around the sun, a region called the heliosphere, where the sun's influence dominates. Inside this bubble, the solar wind is strong enough to push against the interstellar medium and keep it at bay. But as you move farther from the sun, the solar wind spreads out and weakens. Eventually, at a distance of around 120 times Earth's distance from the sun, about 11 to 12 billion miles, the pressure of the solar wind equals the pressure of the interstellar medium pushing back. That's the heliopause. Beyond that point, the solar wind can't push anymore, and the interstellar medium takes over. Only two human-made objects have crossed the heliopause, Voyager 1 and Voyager 2. These spacecraft, launched in the late 70s, have been travelling outward for over 4 decades. Voyager 1 crossed the heliopause in August 2012, becoming the first human object to enter interstellar space. Voyager 2 followed in November 2018. Both spacecraft are still operational, still sending back data from beyond the boundary, though their power supplies are fading and they'll eventually go silent. But for now, they're out there, drifting through interstellar space, farther from Earth than anything we've ever sent. They're proof that the heliopause is real, that you can cross it, that interstellar space is a place you can reach if you travel far enough and wait long enough. 3i Atlas will cross that same boundary, but from the inside going out, which is the normal direction for objects leaving the solar system. Voyager came from inside and crossed outward. 3i Atlas came from outside, crossed inward through the heliosphere, and is now crossing outward again. It's a round trip through the boundary, though calling it a round trip is misleading because it implies returning to a starting point, and 3i Atlas isn't returning anywhere. It's moving to a different region of interstellar space than the one it came from. The trajectory bent around the Sun, so the outbound path is angled differently than the inbound path. If you could trace its full journey from far away, it would look like a curved line passing through the heliosphere, entering from one direction and leaving in another. The crossing of the heliopause won't be an event that 3i Atlas experiences in any meaningful way. There's no sudden change, no jolt, no dramatic shift in environment. The transition is gradual, the solar wind weakens over a large region, and the interstellar medium gradually becomes more dominant. There's a zone called the heliosheath, the outer layer of the heliosphere, where the solar wind is turbulent and compressed as it meets the resistance of the interstellar medium. 3i Atlas will pass through this zone, and eventually it will reach a point where the solar wind is no longer measurable, where the particles around it are mostly from the interstellar medium rather than from the Sun. That's when it will technically be in interstellar space again, but here's the thing, 3i Atlas won't notice. It has no instruments, no sensors, no way to detect the difference between being in the heliosphere and being in interstellar space. It's just a rock moving through a vacuum, and whether that vacuum is filled with solar wind particles or interstellar particles makes no difference to its trajectory. The object will continue moving at the same speed, in the same direction, following the path determined by the gravitational influences it experienced when it passed through the inner solar system. Crossing the heliopause is significant to us because it's a conceptual boundary, a way of marking where our solar system ends. But to 3i Atlas, it's nothing, just another point along an endless journey. We won't witness this crossing. By the time 3i Atlas reaches the heliopause, it will be decades from now, long after we've lost the ability to observe it. We'll know it happens, or rather, we'll know when it should happen based on our trajectory calculations. We can predict that 3i Atlas will reach the heliopause around a certain year, give or take some uncertainty in the exact distance to the boundary, but we won't have confirmation. There won't be a Voyager-style moment where we receive data from the object as it crosses. 3i Atlas is silent. It has no transmitter, no power source, no way to communicate. It's just moving, and we're just calculating where it should be. And beyond the heliopause lies interstellar space, the true expanse between stars. This is where 3i Atlas came from, and this is where it's returning. But the interstellar space it's heading toward is different from the interstellar space it came from, not in nature, but in direction. It's moving toward a different part of the galaxy, a different region of the sky, a different neighbourhood of stars. And once it crosses the heliopause, once it leaves the Sun's influence behind, it will be truly on its own, no longer a visitor to our solar system, but a wanderer in the galactic void. The Voyager spacecraft gave us our first direct measurements of interstellar space, and what they found was fascinating. The interstellar medium is not empty. It's a plasma, a thin soup of charged particles, mostly hydrogen and helium, mixed with traces of heavier elements and dust grains. The density is incredibly low, far lower than the best vacuum we can create in a laboratory. In a given volume of space the size of a room, there might be just a few dozen atoms, but over vast distances those atoms add up. The interstellar medium has structure, with regions of higher and lower density, shock waves from ancient supernovae, magnetic fields threading through it, cosmic rays zipping through at near light speed. It's a dynamic environment, just extremely diffuse. 3i Atlas will spend the rest of eternity in this environment. It will drift through the interstellar medium, occasionally encountering a dust grain, bathed in cosmic radiation, moving through magnetic fields that have no meaningful effect on its trajectory. The object will be cold, far colder than anything on Earth. Without the sun's warmth, without any internal heat source, 3I Atlas will cool to a temperature just a few degrees above absolute zero, the background temperature of space itself. At that temperature, all chemical activity stops. All molecular motion slows to a minimum. The object becomes a frozen relic, a piece of rock and ice preserved in the coldest freezer imaginable. But it keeps moving. Temperature doesn't affect inertia. An object in motion stays in motion unless acted upon by a force, and in interstellar space, there are very few forces acting on 3I Atlas. Gravity is still there, the gravity of the galaxy itself pulling everything toward the galactic center. But that's a gentle, constant pull that affects all objects equally. It doesn't slow 3I Atlas down or speed it up relative to other objects in the same region of space. The object will continue moving at roughly the same velocity it has now, tens of miles per second relative to the Sun, for the rest of time. And that's the profound part. The journey doesn't stop. The boundary crossing doesn't mark an ending. It marks a transition, a return to the state 3I Atlas was in before it entered our solar system. It's going back to being an interstellar object, not an exception, but the norm. The months it spent passing through our solar system were the anomaly, the brief detour. The millions of years drifting through interstellar space, that's the main story. And we got to witness a tiny fraction of that story, the part where 3I Atlas passed through our neighbourhood and gave us a glimpse of what's out there in the vast spaces between stars. So as we imagine 3I Atlas moving toward the heliopause, getting farther from the Sun every second, we're imagining an object approaching a threshold that will take it out of our world and back into the larger galaxy. We're watching, from a great distance, through calculation rather than observation, as something leaves the last traces of our solar system behind and returns to the infinite. Interstellar space is empty in a way that's hard to comprehend. We use the word empty casually, talking about empty rooms or empty parking lots, but those places are full compared to the space between stars. A room you call empty is packed with air molecules, trillions upon trillions of them in every breath. An empty parking lot still has air, light, warmth from the ground, sounds from distant traffic. But interstellar space is empty on a level that defies intuition. It's a vacuum so complete that there might be only one atom per cubic centimetre, sometimes even less. For comparison, the air you're breathing has about 10 billion trillion molecules per cubic centimetre. The difference is staggering. Interstellar space is as close to absolute nothingness as anything in the universe gets. And this is where 3I Atlas will spend eternity. Not in the bustling environment of a planetary system, not in the relatively crowded space of a solar system where planets and moons and asteroids orbit, but in the vast emptiness between stars. The object will drift through this void, covering unimaginable distances, passing through regions of space where nothing interesting has happened for millions of years, and nothing interesting will happen for millions more. This is the default state of the galaxy. Most of the volume of the Milky Way is interstellar space, empty regions far from any star. The stars themselves, the planets, the nebulae, all the interesting stuff we see in astronomical images, those are tiny islands scattered through an ocean of emptiness. And 3I Atlas is returning to that ocean. What does it mean to drift through interstellar space for millions of years? What happens to an object in that environment? Let's start with the obvious. Nothing. Nothing happens. There's no weathering, no erosion, no chemical reactions, no geological activity. On Earth, rocks change over time. Wind and water wear them down. Temperature variations cause cracking. Chemical reactions alter their composition. Life can colonize their surfaces. But in interstellar space, none of that exists. There's no air, no water, no temperature variation that matters, no life. The object is frozen at a temperature close to absolute zero, and at that temperature, atoms barely move. Chemical reactions require energy, and there's no energy available. So the rock stays exactly as it is, frozen in time, unchanging. The only things acting on 3I Atlas in interstellar space are cosmic rays and the occasional dust grain. Cosmic rays are high-energy particles, mostly protons, that zip through space at near light speed. They come from supernovae, from the remnants of exploded stars, from exotic objects like pulsars and black holes. These particles constantly bombard everything in space, and over time they can cause damage at the atomic level. They can knock atoms out of place, create defects in crystal structures, even transmute elements through nuclear reactions. But these effects are incredibly slow. We're talking about changes that accumulate over millions of years, changes that would be undetectable in any human time frame. 3I Atlas will be slowly altered by cosmic ray bombardment, but so slowly that it's almost meaningless. Dust grains are even rarer encounters. Interstellar space does contain dust, tiny particles of carbon, silicates, and other materials left over from stellar processes. But these grains are so spread out that an object could travel for thousands of years without hitting one. When a collision does happen, it's at high relative velocity, which means the dust grain impacts the surface with a tiny burst of energy, creating a microscopic crater. Over millions of years, these impacts might sandblast the surface of 3I Atlas at the atomic level, but again, this is an effect so gradual it's almost negligible. The object is essentially preserved, a fossil from the time it formed, carried through space with minimal alteration. But while the object itself doesn't change much, its journey continues. 3I Atlas is moving, and that motion is relative to the structure of the galaxy. The Milky Way is a rotating disk of stars, gas, and dust, all orbiting the galactic center. The Sun orbits the galactic center too, taking about 200 million years to complete one orbit. 3I Atlas, now that it's leaving the Sun's influence, is on its own orbit around the galactic center. That orbit is determined by its position and velocity within the galaxy. It will take hundreds of millions of years for 3I Atlas to complete one orbit, and during that time, it will pass through different regions of the galaxy, regions with different densities of stars, different amounts of interstellar gas, different environments. But here's the key thing. Even though 3I Atlas is moving through the galaxy, it's not moving toward anything specific. There's no destination, no target, no endpoint. It's just moving, carried by the momentum it has, following the gravitational gradients of the galaxy. It might pass relatively close to other stars eventually. It might spend long stretches in the voids between spiral arms, regions where stars are sparse and space is even emptier than average. It might pass through molecular clouds, dense regions of gas and dust where new stars are forming, though even dense in this context means densities far lower than the best vacuum on Earth. These passages through different environments won't change the object much, but they add variety to the journey, a sense that the interstellar medium isn't uniform, that there are different neighbourhoods in the galaxy, and time becomes something different in interstellar space. On Earth, we measure time in seconds, minutes, hours, days, years. These units make sense for human life, for the pace of events we experience, but in interstellar space those units are almost meaningless. A year passes and nothing changes. 1,000 years pass and 3I Atlas looks the same, moves the same, exists the same. 1,000,000 years and still the object is just drifting, frozen, silent. Time stops being a measure of change and becomes just a measure of duration, of how long something has existed in a static state. And for 3I Atlas, that duration is effectively infinite. There's no end to this journey, no terminus, no final act, just endless drifting through the galaxy, through the void, through the darkness. It's hard to find meaning in that. We're used to stories with beginnings, middles, and ends. We're used to journeys that lead somewhere, that have purpose or direction. But 3I Atlas's journey has none of that. It's pure existence without purpose, motion without destination, time without change. And yet, there's something profound in that too. It's a reminder that the universe doesn't operate on human narratives. Most of what exists is indifferent to meaning, to purpose, to the stories we try to impose on it. 3I Atlas is just an object moving through space, and that's all it needs to be. The fact that we briefly observed it, briefly wondered about it, briefly felt a connection to it, that's our story, not the object's. But even in the vast emptiness of interstellar space, even in the timescales that dwarf human comprehension, there's the possibility of change. Not change to the object itself, but change in its circumstances. There's the possibility, however remote, that 3I Atlas will someday encounter another star system, that it will pass close enough to a star to feel significant gravitational pull again, to enter another solar system, to pass by other planets. The odds are low, incredibly low, but they're not zero, and that possibility, that tiny chance of another encounter, is worth exploring, because it's the closest thing to a future event in 3I Atlas's endless journey. Here's the question that everyone wants answered, the question that carries a kind of cosmic hopefulness. Will 3i Atlas ever reach another star system? Will it someday pass through another solar system the way it passed through ours, giving some other world, some other species if they exist, a chance to observe an interstellar visitor? It's a beautiful thought, the idea of this object as a perpetual wanderer, drifting from star to star, an eternal messenger of the galaxy. But the reality is complicated, and the answer is, we don't know, and even if it does, we'll never know about it. Let's start with the distances involved. Stars are far apart. The nearest star to the Sun, Proxima Centauri, is about 4 light-years away. A light-year is the distance light travels in 1 year, which is about 6 trillion miles. So Proxima Centauri is roughly 25 trillion miles from us. That's the nearest star, and it's unimaginably distant. The average distance between stars in our region of the galaxy is even greater, more like 5 or 6 light-years. And the galaxy is full of stars, about 100 billion of them, scattered across a disk that's 100,000 light-years in diameter. The volume of space is enormous, and the stars, despite their numbers, are spread so thin that the galaxy is mostly empty space. 3i Atlas is moving at tens of miles per second. That sounds fast, and it is by human standards. But on the scale of interstellar distances, it's incredibly slow. Let's say 3i Atlas is moving at 30 miles per second relative to nearby stars, which is a reasonable estimate. At that speed, how long would it take to travel 1 light-year? Light moves at about 186,000 miles per second, which means a light-year is 186,000 times 60 seconds, times 60 minutes, times 24 hours, times 365 days. That's about 6 trillion miles. At 30 miles per second, 3i Atlas travels about 1 billion miles per year, which is fast on solar system scales, but incredibly slow on interstellar scales. It would take about 6,000 years to travel 1 light-year. To reach Proxima Centauri, the nearest star would take about 25,000 years. And that's only if 3i Atlas happened to be heading directly toward Proxima Centauri, which it's not. We don't know exactly where 3i Atlas is heading in the long term because we can't predict its trajectory with that level of precision over such long timescales. Orbital mechanics works well for short timescales, decades or even centuries, but over millions of years, small uncertainties accumulate. The gravitational influence of other stars, the complex structure of the galaxy, the movement of the spiral arms, all of these factors introduce uncertainties. We can say generally what direction 3i Atlas is heading, but we can't predict whether it will pass close to any particular star in the distant future. It's heading toward a region of the sky, but that region contains many stars, and whether 3i Atlas will come close to any of them is a matter of probability, not certainty. And the probability is low. Space is so vast, and stars are so small in comparison, that random trajectories are unlikely to bring an object close to a star. Think of it like throwing a dart at a map of the entire Earth and trying to hit a specific city. The odds are not in your favour. Now imagine the map is 3-dimensional, the size of a continent, and the cities are scattered randomly throughout the volume. That's closer to the reality of interstellar navigation. Yes, there are 100 billion stars in the galaxy, but they're distributed through an enormous volume of space, and the odds that any given trajectory will pass close to one of them are very low. But here's the thing. Over long enough timescales, unlikely events become probable. If 3i Atlas drifts through the galaxy for 100 million years, for 1 billion years, the odds that it will pass relatively close to another star increase. We're not talking about a direct hit or even a close approach like it had with Earth. We're talking about passing within a few light-years of another star, close enough that the star's gravity might perturb the trajectory slightly, close enough that if the star has planets, and those planets have observers, they might detect 3i Atlas if they're looking. The probability of such an encounter over the lifetime of the galaxy is not zero. It's low, but it's not zero. And if such an encounter happens, what would it look like? Imagine a civilization on a planet orbiting another star. They have telescopes, they study their sky, they track objects in their solar system. One day, they detect something unusual, an object approaching from interstellar space, moving on a hyperbolic trajectory, clearly not bound to their star. They observe it, study it, measure its composition and velocity and trajectory. They realize it's a visitor from another star system, a piece of another world passing through their neighbourhood. They watch it approach, make its closest pass, and then leave, heading back out into interstellar space. They publish papers, debate its origin, wonder if other civilizations have observed it too. And then it fades from their view. continuing its journey, and they move on with their lives, carrying the memory of that brief encounter. Sound familiar? That's what we just experienced with 3i Atlas, and it's possible, however remote, that the same story will play out again someday, somewhere else in the galaxy, with 3i Atlas as the visitor and some other civilization as the observers. It's a poetic thought, the idea that this object could be a messenger, a traveller, that connects different star systems not through intentional communication, but simply by existing and moving through the galaxy. Each civilization that observes it gets a glimpse of what's out there in the larger cosmos, a reminder that they're not alone in the galaxy, even if they never meet or communicate with each other. But we have to be honest about the uncertainties. We don't know if 3i Atlas will ever encounter another star system. We don't know if any such system would have planets, or if those planets would have life, or if that life would be capable of observing and understanding what 3i Atlas is. We don't know if 3i Atlas will survive its journey intact. Over hundreds of millions of years, the object might be eroded by cosmic rays, might collide with something and be destroyed, might be perturbed by gravitational interactions and sent on a different trajectory. There are so many unknowns, so many variables we can't account for. The future of 3i Atlas is a mystery, and it will remain a mystery forever, because we'll never get confirmation of what happens to it, and maybe that's okay. Maybe the uncertainty is part of the beauty. We observed 3i Atlas for a brief window of time, gathered data, learned what we could, and now it's gone from our view, continuing a journey we can only imagine. We've added to the story of this object, contributed our chapter, and now the story continues without us. Somewhere out there, 3i Atlas is moving through the void, heading toward a future we can speculate about but never know. And that's the nature of cosmic exploration. We get glimpses, we learn what we can, and we accept that the universe is full of things beyond our reach, beyond our knowledge, beyond our ability to follow. So could 3i Atlas reach another star? Maybe. Probably not in the near future, but over millions of years, over the vast timescales of the galaxy, it's possible. And if it does, we'll never know. But the fact that we can ask the question, the fact that we can imagine that future, is a testament to our curiosity and our desire to connect with something larger than ourselves. As 3i Atlas fades from view, as it continues its journey into the outer solar system and eventually beyond, we're left with the question of what it leaves behind. Not physically, because the object didn't deposit anything here, didn't leave a chunk of itself on Earth or in our orbit. But in terms of knowledge, in terms of impact, in terms of the human experience of observing something from beyond our solar system, what did we gain from this encounter? What does 3i Atlas leave behind in our world? The most obvious answer is data. Thousands of observations, images captured by telescopes around the world, spectra that reveal the object's composition, measurements of its trajectory and velocity and rotation. This data is stored in archives, in databases, in the hard drives of universities and observatories and space agencies. It's a resource that scientists will be analysing for years, extracting insights, comparing it to other objects, refining our understanding of what interstellar visitors are like. Every observation of 3i Atlas adds to the broader dataset of interstellar objects, a dataset that's still incredibly small. We've only observed a handful of these visitors, Oumuamua in 2017, Borisov in 2019, and now 3i Atlas. Each one is unique, and each one teaches us something new. From 3i Atlas, we learned about the behaviour of interstellar comets. We saw how it became active as it approached the Sun, how it developed a coma and tail, how its brightness changed with distance. We measured its composition, finding water ice and other volatile materials, confirming that at least some interstellar objects are similar to the comets in our own solar system. We tracked its trajectory with precision, confirming that it's on a hyperbolic orbit and will leave the solar system. We studied how it fragmented, how pieces broke off during its close approach to the Sun, and what that tells us about the structural integrity of interstellar objects. All of this information contributes to our understanding of the galaxy, of how material moves through interstellar space, of what the building blocks of planetary systems look like beyond our own. But the legacy of 3i Atlas goes beyond data. It's also about preparation. Every interstellar visitor we observe helps us prepare for the next one. We learn what instruments work best, what observational strategies are most effective, what questions we should be asking. We improve our detection systems so we can spot these objects earlier, giving us more time to study them before they pass through and leave. We develop better models for predicting their behavior, for understanding how they'll respond to solar heating, for calculating their trajectories with greater accuracy. 3i Atlas is a case study, a real-world test of our capabilities and our limitations, and the lessons we learn from it will make us better prepared when the next interstellar visitor arrives. And there will be a next one. That's one of the surprising things we've learned from the recent wave of interstellar object discoveries. They're not as rare as we thought. For most of history, we assumed interstellar objects were incredibly rare, that encountering one was a once-in-a-lifetime event if it happened at all. But the detection of Oumuamua, Borisov, and 3i Atlas within just a few years has changed that assumption. It suggests that interstellar space is full of these objects, that they're constantly passing through the galaxy, and that we're only now developing the technology to detect them. Better telescopes, automated sky surveys, improved algorithms for identifying unusual trajectories, all of these advances are making it possible to spot objects we would have missed in the past. So we can expect more interstellar visitors in the future, more opportunities to study them, more chances to learn about the galaxy beyond our solar system. But beyond the scientific legacy, there's also the human legacy. Millions of people around the world followed the story of 3i Atlas. They read articles, watched videos, looked at images, asked questions. They felt a connection to this visitor from another part of the galaxy, a sense of wonder at the fact that something from so far away had come so close. For a few months, 3i Atlas was part of the global conversation, a shared experience that transcended national borders, languages, and cultures. People in different countries, with different backgrounds, were all looking at the same object, all marvelling at the same cosmic event. There's something unifying about that. In a world that often feels divided, where conflicts and differences dominate the headlines, astronomy has a way of bringing people together. When we look at the sky, when we contemplate the cosmos, our human differences seem smaller. We're all inhabitants of the same planet, all witnesses to the same universe, all participants in the same cosmic story. 3i Atlas reminded us of that. It reminded us that we're part of something much larger than our daily lives, much larger than our individual concerns. We're part of a galaxy full of objects and systems and processes that have been unfolding for billions of years, and we get to witness tiny pieces of that story. And that's the real legacy of 3i Atlas. The reminder that we're not alone in the universe, not in the sense of intelligent life, but in the sense of being surrounded by a vast and dynamic cosmos full of things to discover and understand. Every interstellar visitor is a messenger, not carrying information in any intentional way, but carrying the reality of the galaxy to our doorstep. These objects exist because the galaxy is full of material, because stars form and die, because planetary systems form and sometimes eject objects, because gravity and motion and time create an environment where things drift through space for millions of years. And when one of those things happens to pass through our solar system, we get a glimpse of that larger reality. As 3i Atlas continues its journey, as it moves farther from the Sun and from Earth, as it crosses the heliopause and returns to interstellar space, we're left with gratitude. Gratitude for the fact that we were here at this moment in history with the technology and knowledge to observe and understand what was happening. Gratitude for the astronomers who dedicated their time to tracking this object, for the scientists who analysed the data, for the educators and communicators who shared the story with the public. Gratitude for the fact that we live in a time when we can detect objects from interstellar space, when we can measure their composition and trajectory, when we can piece together their histories and predict their futures. And gratitude for the reminder that the universe is full of wonders, that there are things happening in the cosmos that we can barely imagine, that our moment of existence coincides with an era of discovery and exploration that would have seemed like magic to previous generations. We get to witness interstellar visitors passing through our solar system. We get to see images of distant galaxies captured by space telescopes. We get to study the formation of stars and planets, the behaviour of black holes, the expansion of the universe itself. We're living in an age of astronomical discovery, and 3i Atlas is part of that story. So as we say goodbye to 3i Atlas, as we watch it fade from view and continue its journey into the cosmic dark, we carry with us the knowledge that we were part of its story, however briefly. For a few months, our paths crossed, our worlds intersected, and we learned from each other. We learned what an interstellar visitor looks like up close. We learned that the galaxy is full of these objects drifting through space, carrying the history of their formation. we learned that our solar system is not isolated, that we're part of a larger galactic ecosystem where material moves between star systems over vast timescales. And 3i Atlas, if it could somehow carry memory or meaning, would know that for a brief moment it was observed, studied, wondered about by a species on a small planet circling a medium-sized star. That for a few months it was the focus of attention, the subject of curiosity, the centre of a shared human experience. And then it continued on, as it always was going to, as physics demanded, as the trajectory determined billions of years ago required. It left us behind, not through any choice or intention, but simply because that's what objects on hyperbolic orbits do. They pass through and they leave. We were a brief interruption in an eternal journey. For a moment, 3i Atlas was illuminated by our telescopes, visible to our instruments, present in our awareness. And then it returned to the darkness, to the void, to the endless drift through interstellar space. And we're left here, on our planet, looking up at the sky, knowing that somewhere out there, getting farther away every second, an object from another part of the galaxy is continuing a journey that will outlast our civilization, our species, perhaps even our planet. And that's beautiful in a way. That's the poetry of astronomy. We're temporary, but the cosmos is vast and enduring, and we get to witness tiny pieces of its story before we fade away. So thank you, 3i Atlas, for passing through. Thank you for giving us a glimpse of the interstellar void, for reminding us of the scale and beauty of the galaxy, for connecting us, however briefly, to something beyond our world. We'll carry the memory of your visit, the data you allowed us to gather, the wonder you inspired, and we'll be ready when the next visitor arrives, better prepared, more knowledgeable, more grateful for the opportunity to witness the cosmos in motion. Where is 3i Atlas going now? It's going home, back to the stars, back to the infinite, back to the eternal drift through the galaxy, and we'll be here, watching the sky, waiting for the next visitor, carrying the stories of the ones who came before.